Dear friends, welcome you again to my class. In previous class, we have discussed about vapor power cycle and how to represent this vapor power cycle on TF diagram, PV diagram, and HF diagram. And we have also discussed how to find out thermal efficiency of the vapor power cycle based thermal power plant. So again, we are going to discuss and discuss करेंगे. We are going to discuss about how to find out thermal efficiency and how to define mean temperature and how mean temperature defining parameter for operation of the thermal power plant. How this mean temperature fixes maximum pressure limit and how we can further expand maximum pressure limit and temperature by using reheat cycle. So these are topics that we are going to discuss in next videos. So first we discuss what is steam rate and what is your work ratio. That I want to define work ratio because apart from thermal efficiency we can also define the performance of the thermal power plant by work ratio and steam rate. So let us first draw a TF diagram. Same thing we can represent on HF diagram also. So same cycle we can represent on TF diagram and HF diagram. These are two most frequently used cycles for solving the vapor power based problem of thermal power plant. So you must have practice of TF diagram and HF diagram. So one thing again I want to define here in terms of the how we can find out pump work. These are two cycles. Pump work can be defined as we have defined pump work WP equal to H4 minus F3. And we know that process 3-4 is under ideal condition. Process 3-4 are isentropic process. And for isentropic process, we have defined by property DH equal to TDS plus VDP by using this property using Maxwell relations and TDF diagram, TDS equation. So DH can be defined as TDS plus VDP, and we know that this process C4 is an isentropic process. So DS is 0. For isentropic process, DS is 0. DS is 0. So DH equal to VDP, and DH means H4 minus F3, that is a pump work WP equal to VDP, and V is a specific volume of the water at this point. You can say V and P2 P1 minus P2. So this work is actually minus sign, negative sign, because we are doing work is supplied from outside. So this work is V delta P, that is we take negative, and you can see V P1 minus P2 into 10 to the power 5 joule, provided that P1 minus P2 should be in bar. You can use this equation directly. If P1 and P2 are given in bar, then you can use this equation to find out work done in running the pump. So this work is very small compared to turbine work, because here specific volume at liquid state is very small. Because it is highly compressed. So liquid state specific volume of water is very small, and compared to it is in gaseous state. That's why that is the beauty of the vapor power based thermal power plant, because it is a Rankine cycle. That is the beauty of Rankine cycle, because here pump work is very small. If it is a fluid is in gaseous state, then work that we get from the turbine will be less than work that we needed to run the compressor. If this fluid 3-4 will be handled by the pump in gaseous state, then work that we get during expansion of the turbine will be less than work required to pump back the same gaseous state fluid from 3-4. That's why, because first we condense it in condenser, so that pump work will be very less. Pump work WP will be very less compared to WT. That is a advantage of using Rankine cycle. This is very important question that most frequently asked in interview and theoretical discussion IES examination also. So many examinations, this question will be asked. Why Rankine cycle is more popular compared to other Brayton cycle or gas power? So here let us define what is steam rate. Already we have defined thermal efficiency and thermal equal to WT minus WP upon Q1. These are already defined, and WT minus WT, it is a W net equal to WT minus WP in terms of the kilojoule. So one more important thing that is parameter is work ratio. What is your work ratio? Work ratio. What is your work ratio? Work ratio. WR. It is ratio of W net upon WT means WT minus WP upon WT, always less than 1. So this define how much this thermal system is efficient, because lesser the value of WT, work ratio will be higher and higher, and it is reaching to unity if WP becomes 0. So work ratio is important parameter define performance of the thermal power plant. Another parameter is a steam rate. This is also very important. What is a steam rate? Steam rate SR. It is defined as ratio. It is defined as kg of steam required per hour. Kg of steam required per hour to produce 1 kilowatt of power. It is kilogram of the steam required per hour to produce 1 unit of the power. Means W net कितना होगा? W net equal to 1 kilowatt. kg of steam required per hour to produce 1 kilowatt of power per hour. 1 kilowatt of power. That is 1 kg. Means we are using WT minus WP, W net for 1 kg of load to that. So 1 kg upon WT minus WP. This is a net work. WT minus WP. 1 kg upon, this is a kilojoule. So divide whole numerator and denominator by second. 1 kg per second and 1 WT minus WP kilojoule per second. So this will become 1 kg per second and WT minus WP kilowatt. So multiplied by 3600. So second, if you, because we have to find out this value in hour, multiplied by 1 kg multiplied by 3600. 1 hour equal to 3600 seconds. WT minus WP kilowatt. Here kilowatt second, now kilowatt hour. So this is steam rate. Steam rate is defined as 3600 upon WT minus WP kilowatt hour. You can use this equation for finding out steam rate. So this is all about these are various parameters. Find out thermal efficiency, work ratio, steam rate, and next we will discuss what is mean pressure, mean temperature. Next topic is mean temperature, and what is need of defining mean temperature. T mean. What is need of defining mean temperature? So again we will use a TF diagram, TS diagram to define mean temperature. So this is a cycle. You see that 1 to 2 is expansion in turbine WT. Now turbine work you will get in process 1 to 2 isentropic expansion, and 2 to 3 is a condensation process at pressure P2, and 4 to 1 is a constant pressure heat addition process. Constant, but temperature is varying here. You can see temperature is varying. Temperature is not constant. So how we can define a constant temperature? Suppose there is we imaginary temperature. We know that heat addition process whole area will come under this one. This is the whole area in heat addition process. So we take it mean temperature in such a way that area under the curve 1, 2, 4 already we have taken 5, 6. Area under the curve 1, 2, 5, 6 and 4 is same, that equal to area under mean temperature. If it suppose we consider that instead of at varying temperature we are adding heat. We are adding heat here Q1 at varying temperature, but pressure is constant. Now we consider that temperature is constant, so that area earlier and area after that Both are same area. So we consider a mean temperature. Suppose we take by another color mean temperature. Here this is a mean temperature. This is a T mean. This is a T mean temperature. T mean temperature under this curve. This curve area under the curve. This is a, you can say 1 dash and 4 dash. Area under the curve 1 dash 4 dash is same as area under the curve 1 5 6 4. So heat addition, you know that heat addition process Q1 equal to, now Q1 equal to, so Q1 equal to, now Q1 equal to, you see Q1 equal to U by using Q equal to Ts. So T mean into S means here temperature entropy difference, S5 minus S6, S5 minus S6, and Q2 is heat rejected. That is a Q2. Q2 is heat rejected. That is that this temperature is same for both. That is a T2. So T2 is heat rejected means T2 entropy limit are same, S5 minus S6. So W net is, you know, W net equal to Q1 minus Q2, Q1 minus Q2 equal to S5 minus S6 and Tm minus T2. So N thermal equal to W net upon Q1 equal to S5 minus S6 Tm minus T2 upon S5 minus S6 into Tm. This will be removed. So equal to Tm minus T2 upon Tm. So 1 minus T2 upon Tm. You know that this T2 is a condenser temperature and it is constant. Heat rejected, this is not varying. Heat rejected in condenser is constant. Only there that varying is a Tm. That Tm is varying. So N thermal is a function of only temperature Tm. Higher the temperature, you see higher the temperature, higher will be efficiency, higher will be thermal efficiency. So thermal efficiency and performance of thermal power plant based only on the mean temperature. It is a function of thermal efficiency, and thermal efficiency is a function of mean temperature only. Higher the mean temperature, higher will be the thermal efficiency. So what are limit of the increasing mean temperature? Because of the thermal stresses, we can't increase the temperature beyond, because various components that will be exposed to the steam, higher temperature steam. These components are superheaters, steam turbines, insulation, boiler chamber where steam is accumulated. All these chambers will be exposed to higher temperature and they have to bear higher thermal stresses. That's why mean temperature means maximum temperature limit is fixed one. You can't go beyond approximately 550 degrees centigrade. You can't go beyond that, otherwise it will become very, very costly, because you have now use very high temperature bearing materials, very advanced materials which are now used in jet turbines and spaceship. So it become very, very uneconomical. System become very, very uneconomical. That's why temperature limit is fixed one. So if temperature limit is fixed, then what we can do? Next we see what we can do. If temperature limit is fixed, then we will try increase the pressure. So we will see what is impact of increasing pressure. By increasing pressure we can increase the mean temperature. So see here impact of increasing temperature. Already we know that temperature limit is fixed. At this point, quality should not be 0.8, less than 0.85. Temperature limit, we first will meet T maximum. T maximum means 550 degrees centigrade. Once we fix temperature, what we can do? We can increase pressure. This is a P2 and this is a P1. By increasing pressure, we can increase the mean temperature. So you can see what will happen if we increase the temperature. Pressure. This is a P2. P2 higher than P1 dash. This is a P1 dash higher than P1. So if you can see here, if you are increasing pressure, then mean temperature will be higher for this pressure. Mean temperature earlier, suppose earlier was mean temperature was that one. This was earlier mean temperature Tm1, and for that mean temperature will increase. And for this one, mean temperature will slightly increase Tm2. If we increase pressure, mean temperature will increase. But what will happen here? You see, by increasing mean pressure, if you expand steam from here to here, quality of the steam is decreasing. You see that quality of steam is decreasing. X to S dash. This quality is decreasing, and we know that if quality of steam, more moisture content will there after expanding from turbine, and when moisture content will increase, expanding exhaust steam from the turbine will erode the blades of the turbine. That is a major constant. If you increase pressure, mean temperature will increase. There is no doubt mean temperature is increasing. But what is happening here, if you expand steam in turbine from this point to this point, quality of steam is decreasing. Here we already fixed quality of steam 0.85. Suppose here quality of steam becomes 0.75. This is not acceptable, because if moisture content is more, leaving steam from having high moisture content from the turbine will erode, destroy the blades of the turbine. These are highly costly blades. You need frequently replace these blades, and damage will occur. And if there is more moisture, lesser quantity of the steam is available for the generation of power. So power generation will also decrease, and life of the steam turbine will also decrease. So that is not acceptable. So maximum pressure and maximum temperature is also fixed because of the moisture content. Maximum temperature is fixed because of the thermal stresses that material has to bear, and maximum pressure is fixed because of the steam quality that should not be lesser than 0.85. So for single stage turbine, we can't go beyond 500 degrees centigrade, and pressure should not be higher than 20 megapascal. 20 megapascal is the maximum pressure limit under which single stage turbine can work. So there is an option. If we further want to increase pressure to get more power, we have to use reheat cycle. And reheat cycle we will discuss in our next lecture. So this is a discussion why maximum temperature and maximum pressure for single stage steam turbine, vapor power cycle based steam turbine is fixed one. This is very important discussion, and you must know. And we will also solve some question for, because these cycles we have described based on only ideal condition. We have considered that expansion taking place isentropic in turbine, and compression is taking place in pump, that is also isentropic, but this is not actual. These compression and expansion processes are not isentropic, but these are in real compression and expansion. Due to irreversibility, entropy will increase, so these are not isentropic. We have to consider pump efficiencies and thermal turbine efficiencies, and under actual condition we will solve question. So it will become very clear when we solve question for actual cycles. In next class we will solve some questions so that concept become clear, and then we go for the reheat cycle. Thank you very much for watching my video. Please like and comment.